I can just share my screen.
Yeah. Okay. All right. So hello, everyone. I hope that everyone is doing fine and everyone is healthy. So welcome to the edition of this ICTS seminar. And today we have the pleasure to have Professor Douglas Stanford from Stanford University. And he's going to tell us about the density matrix of Hawking radiation. So Douglas, over to you.
Okay, thanks. Yeah, thank you for the invitation. It's a pleasure to be giving this talk. So this talk is going to be sort of an expanded version of the second half of the talk that I gave last week at Strings. And so to start, there have been these interesting recent calculations that have got the page curve of an evaporating black hole using semi-classical gravity. So that was worked out in these papers by Pennington, by Almhary, Engelhardt, Marolf, and Maxfield.
I'm sorry, Douglas. So we cannot see your screen. I don't know. At least.
Oh no.
From my
Uh-oh.
Yes, I can. Ah, good.
Yeah, we can't. I can't.
Uh-oh. Can you see it now?
Not yet.
It came and went away, Douglas.
Oh,
now
I know what
there.
the problem is. Sorry, I know what the problem is. Sorry. Okay, this is gonna be better. Now, how about that?
Yeah, now it's there.
That's good.
Okay. Okay. Yeah, thanks for letting me know. That would have been a really boring talk otherwise. So recent calculations have got the page curve using semi-classical gravity. And this is kind of interesting and surprising because a density matrix rho r, so rho sub r means the density matrix of the radiation of an evaporating black hole. And a density matrix rho r that follows Hawking's formula for the entropy can be very simple. You can have a very simple density matrix that does that. Basically, the density matrix is just a thermal density matrix. But a density matrix that follows Page's curve will be full of structure and complicated numbers. It's kind of like a pure state. A typical pure state is a complicated object, much more complicated than the thermal density matrix. So it's kind of puzzling because a density matrix that follows Page's curve should be very complicated. But semi-classical gravity, the tool that was used to compute the Page curve here, semi-classical gravity is not, it's a simple theory, and it doesn't seem to be rich enough to describe a complicated object like a density matrix that follows Page's curve. It doesn't have enough stuff in it, doesn't have enough complexity. So what's going on with this puzzle? In particular, what happens when you try to compute the density matrix using the same semi-classical methods that give the entropy? The entropy is some kind of function of the density matrix minus trace of rho log rho. And we can compute that in gravity. But what happens if we actually try to compute the density matrix itself? Do we get some complicated object full of interesting numbers? Well, no, surely we can't get that in a simple theory of gravity. But what exactly do we get? So the thing I'm going to discuss in this talk is that what you find when you try to compute the density matrix is that gravity is sort of cheating. Instead of giving the answer for an actual single density matrix, which would be complicated and full of interesting structure, it's describing an ensemble of them, which can be simple. So as an example of this, if you could imagine, let's imagine that we are just trying to pick some kind of a vector in a very high dimensional space. That vector is described by a long list of numbers, so it's a complicated object. But you could easily describe a probability distribution on vectors in a high dimensional space in a very simple way. And the gravity seems to be using that here. It's describing an ensemble, like a probability distribution on density matrices, which can be simple, even though individual elements of that, individual draws from that ensemble are complicated. Okay, so that's kind of a summary of what semi-classical gravity seems to be doing and how it's able to give the Page curve without having enough complexity to describe a real interesting density matrix. Okay, so okay, so let's start discussing discussing where this ensemble comes from, try to motivate why gravity is describing an ensemble. So here I'm going to review a sort of an old story, which is the connection between space-time wormholes and ensembles. So let's think, to draw the pictures as simply as possible, let's think about ADS2 CFT1. The boundary theory will be one-dimensional, just time. The bulk theory will be two-dimensional. The way the ADS CFT dictionary works is that time contours of the boundary theory become boundary conditions in the bulk that you're supposed to fill in with two-dimensional gravity in some way. So, for example, if we're trying to compute the partition function of the boundary theory, z of beta, that's trace of e to the minus beta h, then the time contour that's associated to that is this circle here. It's the thermal circle, a periodic imaginary time running from 0 to beta. So that's the time contour that is associated to this object, the thermal partition function. Thermal partition function associated to this circular time contour. And ADS-CFT dictionary says to compute that thing using holography, you're supposed to fill in that circle with some kind of gravity configuration. So some two-dimensional gravity configuration, like what we showed on the right here. You start with a circle on the boundary and you fill it in with some two-dimensional geometry. So that's the way the ADS-CFT dictionary works. So now let's take the same dictionary and same procedure, but consider a different quantity. Let's consider z of beta squared. So two copies of the same boundary conditions, two copies of the same time contour in the boundary theory. Z of beta squared is just a product of these two traces. You might expect to get just the product of the same bulk computation that we did before. But there can also be a contribution from a connected geometry. So we can have this thing plus a geometry, this wormhole geometry that connects together the two different boundaries. And there's a contradiction between these two statements, right? So if z of beta is equal to this quantity here, then z of beta squared can't be equal to this quantity on the second line because it has this extra wormhole piece. And this led to a bit of a puzzle. And one resolution, the current way of thinking about this is that you're supposed to interpret the gravity answer as not computing a particular z of beta, but computing an ensemble average of z of betas. So the first diagram here should be interpreted as computing an ensemble average of z of beta, and the second line here should be interpreted as computing the ensemble average of z of beta squared. And now there's no problem with factorization, because ensemble average of z of beta squared doesn't have to be exactly the square of the ensemble average of z. So there's no contradiction for the fact that we have an extra wormhole contribution here in the second line. And in fact, what the wormhole contribution is computing for you is just the variance of z of beta in whatever ensemble gravity is describing. So the wormhole computes expectation value of z beta squared minus the product, this is the square of the expectation value. And so these ideas, yeah, please.
Sorry, maybe I'm asking a little bit early, but the discussion you just gave on this slide, if I just close my eyes and listen to you, it can apply in any dimension, right?
Yeah. Yes.
So this is a possibility in any dimension, including for n equal to 4 super Young's theory and stuff like that.
Yes, that's right.
Dual. Okay. I just wanted to understand that. Okay, thanks.
But sorry again, sorry to interrupt, but can I just make one small comment and then probably
sure.
If you don't mind, Douglas, which is, I mean, it's not clear that the double trumpet will contribute in a general theory. I mean, it could be that Casimir effects, etc., force the throat to pinch off. Isn't that a possibility that you don't have the double trumpet contribution in some cases?
Yeah, that is a possibility. So it's possible that for some reason, you're not supposed to include this diagram at all because of some principle that we don't understand. It's also possible that if you try to compute it, you get 0 sometimes. Or it's also possible that you're supposed to add a bunch of other stuff which cancels it. So as far as I know, those are the only three possibilities that we could have in the case of n equals 4. So it's a really good point to bring up, though, that for some, let's say for n equals 4 Superang Mills, there's no ensemble. So in that case, we'd have to have a different resolution of this puzzle. And as far as I know, the three possibilities are either you're just not supposed to do this calculation at all. That's possibility A. Possibility B is the wormhole is somehow 0. And possibility C is that you're also supposed to add a bunch of other stuff that cancels the wormhole. And I don't know which of those possibilities is correct for n equals 4 Superang Mills.
I'm sorry, could I ask, what, in the old literature and these papers you cited, Coleman and Giddings and Strominger, what attitude did they take to similar questions?
Well, I think Coleman especially was sort of comfortable with the idea that there would be an ensemble. So I think the conclusion that these folks came to is that the wormholes imply that the universe is really describing an ensemble of theories. Then in the third paper by Maldacena and Maus, and in the later paper by Arkani Hamed, Polchinski, and Orgera, these papers were reconsidering these wormholes with the knowledge of ADS-CFT. So they were trying to think of ways why the wormholes could be wrong or could disappear or could not be embedded in a realistic theory. And they did find some problems with wormholes, but in the end, they found examples that they thought made sense. So they were sort of puzzled. These papers end with sort of a puzzle that's unresolved.
Sorry, I have another question here. If we accept that we are supposed to do this trumpet calculation, then it's not clear that an ensemble will resolve all puzzles, right? Because you could try and compute z of beta cubed, and then you could have more complicated wormholes. So is it clear that a single probability distribution will correctly interpret, all of these multi-wormhole contributions? You see what I'm saying?
No,
beta is like sum over average over some partition functions, but then I could try and compute z of beta cubed or z of beta 4. And,
yeah.
Is it clear that the single probability distribution will make all of these answers consistent?
No, it's not clear, but there are examples where it does. So the one example is JT gravity, and there, the problem you're describing is exactly consistent with an ensemble of boundary theories.
Okay.
And you can show that for arbitrary many boundaries and arbitrary genus of wormholes. So it's really true. I'll discuss another example later that, well, might make you believe, in a few slides, I'll discuss another example that might make you believe in the wormhole a little bit more, but maybe not.
Douglas, please do go on. But just at the end, I would appreciate a slightly longer discussion on Coleman, etc.'s ideas, just simply because, those were not on as firm footing in Euclidean gravity as we would have liked. And they also ran into all kinds of problems with large wormholes and so on and so forth. And so I'd be curious to hear what you have to say about it. But let's come back to that at the end. Just flag the issue here.
Okay, I'm not sure. Yeah, I would be interested to hear what you have in mind. I don't know what you're referring to with the large wormholes, but
okay, yeah, please go ahead.
Okay, so
I'm sorry, Douglas. I'm sorry to slow you down, but just as a follow-up to Subrat's question, is there a clear consistency condition you can write down on various z of betas so that it comes from an ensemble? Are there some equations that need to be satisfied so that it comes from an ensemble?
Well, one example is, I guess there are some constraints from positivity. Like you want z of beta to be an integral over some, the answer is to be an integral over some positive measure of quantities that satisfy the rules that you expect. So it is, that is constraining. But there's so much freedom in what you mean by an ensemble that I don't know how to write equations. We could probably write some inequalities. For the case of JT gravity, the way that you show that this is consistent with an ensemble is not by writing down a series of inequalities and showing that gravity satisfies the inequalities. It's, you get lucky, and you can just directly guess the ensemble and prove that the gravity theory is calculating that ensemble. So more generally, I don't know how to answer that question, because in the one example where we understand it really well, we got kind of lucky.
Thank
you. Hello?
Yeah.
Sorry. So is there a string worldsheet analog of this problem? Because there also, in some sense, we are doing worldsheet quantum gravity, right?
Yeah, so these types of diagrams and these types of wormholes look very natural from the perspective of the string worldsheet. The difference is that here we're thinking about the string worldsheet as sort of as a theory of gravity, not as a string in a target space. So we're thinking about the worldsheet as the space-time, and that's really just a difference in perspective. But
so there, like you would think that, so in some sense, the string worldsheet, the genus expansion for the S matrix is also computing something, some boundary observable, right? In some sense, you have a boundary vertex operators or something, and you have like you're computing the S matrix. So this factorization problem, how does it show up? Does that show up in unitary?
Yeah, there it's not supposed to be a thing that factorizes, so there's no problem. It's only when you think about it as being a bulk gravity theory that's described by in some ADS-CFT-like way that you have a factorization problem. So there's no reason in the string worldsheet for wormholes not to contribute. There's absolutely no problem with wormholes from the perspective of the string worldsheet. In fact, you need to have wormholes in order to have a non-trivial S matrix. That it's all about multi.
So perhaps then, then that is probably what we should take the resolution of, that there are wormholes, but somehow we are not, somehow.
Okay, so good. So you say, so let's see. So you say whenever, well, you say what I'm describing here is not a theory of space-time quantum gravity, it's a worldsheet. And we're describing a string theory here, and we shouldn't think about it as a theory of quantum gravity with some kind of a boundary dual. But is that what you're suggesting?
No, what I'm saying is that, like maybe, like when you have these wormhole contributions, maybe we should not literally take this kind of GPPW kind of viewpoint that anything that, that the product is, that this is the product.
Well, but we're just using the rule. We're just using the ADS-CFT dictionary here. So we're not doing anything weird from that perspective.
What I'm suggesting is that maybe we should modify the ADS-CFT dictionary for this kind of things.
So we should modify it. Well, modify it how? Just say don't include wormholes, or?
I don't know, but what I'm saying is that we would not have a problem with it in if we don't have a problem with it in the worldsheet, from the worldsheet perspective, that if we do include it, and that is what we should do to get a unitary theory. Then we should just do in higher dimensional gravity whatever we do with the worldsheet gravity.
Oh, but I see. No, but we're thinking about the gravity theory a different way, like, and it's a way that we're supposed to, well. Okay.
Yeah, this is more a meta question. So yeah.
That sounds it sounds a bit radical to me. I don't know. That sounds like it's sort of throwing out more of ADS-CFT than we probably need to. But I'm not sure. The thing is that part of what I want to explain is that these wormholes actually sort of makes sense in the ADS-CFT interpretation. Like, there is this problem that you have to invent an ensemble, but the answers that you get kind of look meaningful. They look like they're giving the right answers to something. So it makes you believe that you're kind of interpreting it almost right. And you have to understand what's going on with the ensemble, but we're not like completely off base. It's not like we're, in other words, these wormholes give the right contribution to something that's supposed to be a thermal partition function, not an S matrix. Like, they're giving us the right, they're in the right ballpark. Okay, let me try to convince you of that in a couple of slides. So,
hi, sorry, can I ask just one question? So the
yeah, sure.
final reference of Arkani-Hammett-Polchinski, I think they had a paradox, right? That if the dual theory satisfies cluster decomposition, then you can't have the. So is that still, is there some sort of resolution of that now? Or that's
well, this is the same problem. This is a version of the cluster decomposition problem. That it's sort of a simpler version of that same problem, that a wormhole just violates the factorization of z of beta squared equals z of beta squared. So there's a non-trivial connected correlator for z of beta, which is something that should have had no correlator with anything.
So that's a possible resolution to that.
Sorry? Sorry.
This is a possible resolution to that paradox that you can ensemble.
Well, it's just the same paradox. It's the same paradox that they were worried about in this paper, and that Maldacena and Maus were worried about. It's really the same thing.
And sorry, after Alok is done, sorry, I just wanted to make sure.
Yeah, I'm done. Thank you.
And sorry, Douglas, of course you should go on, but just to make sure I understand that, the way it worked in Coleman et al. Story, and I think the way you're also saying it would work, is that by summing over an ensemble, you would restore cluster decomposition, but you would have to do this ensemble average.
No, the cluster decomposition would be violated, but that's okay, because in an ensemble of theories, cluster decomposition is violated.
I see. Okay. I guess locality would be there in each Hamiltonian.
Yes.
But but cluster decomposition. I see. I was thinking of each Hamiltonian as going to the analog of going to a theta vacuum in QCD, where you have cluster decomposition. And then you, if you like, in this case, you sum over different values of the theta parameter.
Yes, but that sum is not going to respect clustering in general. Okay. Even though it's a sum of things that do.
Okay, all right.
Yep.
Thank you.
Okay, so far what I've been saying about these wormholes, as you guys have correctly pointed out, is kind of bad. Like, they're doing something that we don't want, which is that they're forcing us to think about an ensemble in order to resolve the tension near the top of the slide. So, very roughly speaking, it's at this point we would say something like wormholes are bad. We want to get rid of them somehow. But in the last couple of years, we've seen something positive come out of the wormholes, and this has resulted from just like actually trying to compute the answer that the wormholes give in some cases. And what they seem to be describing is they're giving the right answer for something, first of all. And what that thing is in the examples it's been computed, they're giving an ensemble average of the noise in various quantities due to quantum mechanics. So I'll draw you some plots of what I mean by the noise due to quantum mechanics on the next slide. But here I just have some pictures of different wormholes that people have computed in the last couple of years and sort of what they're related to. So this one here, some beautiful work by Blomart, Mertens, Verschelde, and Phil Saad on the late time behavior of two-point functions using a wormhole like this. There's papers on ETH statistics of OPE coefficients, on quantum chaos and 3D gravity, on JT gravity as a matrix integral. and then this one in the bottom left, which I'll describe in a second. So what is this quantum noise that the wormholes are supposed to be describing? So let's imagine that we have some complicated quantum system, but in finite volume. So the spectrum of the Hamiltonian is discrete. And let's imagine that we've zoomed in on some part of the spectrum, and here I've plotted for you the eigenvalues. These are actually eigenvalues taken from some part of the spectrum of the SYK model. So here's some complicated list of real numbers that are the energies of the system. So this is an irregular, discrete set of numbers. And this is the origin of the quantum noise. It leads to erratic, long-time behavior of correlation functions. So for example, let's take this thermal partition function that we were discussing before. It's trace of e to the minus the argument times the Hamiltonian. And let's study it for complex values of the argument. So take it to be beta plus it and study it as a function of t. So that's a sum over all the energy eigenvalues of this exponential here. And it oscillates in time. It's a sum of oscillating phases. And if you just plot it, so here I took a huge set of energy eigenvalues, of which this was a small piece, and I plotted this function, the real part, for some late time. So I took a very large amount of, very large time and zoomed in on the function at some particular place. And it looks like this. It's some kind of interesting, erratic looking function. So this is what I mean by quantum noise. It's some erratic fluctuations that you get from these sort of random phases, random numbers that come from the underlying discrete set of energy levels and other discrete data in the quantum system. So it's some kind of sort of irreducible, small oscillating noise. Okay, so that's what we mean by quantum noise. And in a holographic dual, so let's imagine this is computed in the boundary theory, super Yang-Mills, n equals 4 super Yang-Mills. In a holographic dual description, it's hard to imagine where this complexity comes from, where this interesting, complicated function comes from. And this is a problem that goes back to Maldacena, Barbon, and Rabonovici. And Polchinski, he didn't, as far as I know, read a paper about this, but he was really worried about it. Like he thought that this might be such a problem that it would imply that the gravity description would have to break down somehow. That it's just so hard to imagine how a smooth geometry like a black hole could lead to a crazy function like this one. Okay, so that's quantum noise.
Sorry, the time scale for these oscillations, is that set by e to the power minus the entropy?
So the time scale, the fastest time scale here is going to be the width, the inverse of the width of the canonical ensemble. So it's like the fastest oscillations correspond to the largest differences in energies. And so those are like the largest differences in energies in the canonical ensemble. So they're like, it's like square root of n or something. So square root of n squared. So the time scale of oscillations is fast, but it's not like exponentially fast. But there's all kinds of frequencies. Like that's the fastest time oscillation that has a significant power, but there's oscillations at slow frequencies as well, all the way down to like e to the minus s. So yeah, it's a really interesting function. Okay, so that plot was for a particular Hamiltonian, and even though a particular Hamiltonian has erratic correlation functions like we just plotted, if we take an average, then an average over an ensemble of theories, then we can get a smooth function that one could imagine computing in gravity. So first of all, we should take an average of something that has a non-zero average. If we just try to average the z, the real part of z, the average will be 0 at late times. It's oscillating above and below the real x-axis. So, but if we take the square of it, then it will be non-zero and it will have some non-zero average. And this is what it looks like if you take the same thing and average it over just the original sample. This is just the square of the function on the previous slide. And then if we average it over 10 realizations, let's say of the SYK model, we get this curve. Over 100, we get this curve. Over 1,000, we get this curve here. So it's approaching some smooth function. And I don't know if you can tell by looking at it, but it's growing slightly because this is zoomed in on part of this spectral form factor, a part of it that's known as a ramp, where it's growing linearly. So it has some value and some kind of simple dependence on time. And this, for this range of times, that dependence is just linear in time. So it's some, after averaging over the ensemble, it's some extremely simple function. We started with like god-awful mess here, which is impossible seemingly for gravity to describe. But after averaging over an ensemble, you get like the simplest function known to mankind. So somehow the lesson of this is that ensemble averaged quantum noise is simple, and simple enough that gravity certainly stands a chance of describing it. And in fact, you do get this simple answer. You get the right answer from a wormhole. That's this wormhole here. So this is what I mean when I say that the wormholes are giving the right answer to something. They're giving the right answer. Yeah, please.
Can I just, so in the previous slide, can you go back to the previous slide? So the previous slide somehow reminds you of, as you know from your work also, of a energy spectrum in random matrix theory, which is supposed to mimic a highly chaotic system of Hamiltonian.
Yes.
So if chaos is somehow a feature of theory of gravity, as you have shown with other authors, wouldn't it not actually, what shall I say, strongly suggest that what you're saying is actually true in general? Because if you expect this type of spectrum, let's say in n equal to 4 Yang-Mills theory, that it's very likely actually that in the very large n limit, this type of very chaotic spectrum will emerge. And so would that not be a hint actually for implication on the gravity theory? This is going back to the questions that many of us were discussing just a few minutes ago. I just wanted to,
yeah. And if so, you're right. So let's take n equals 4 super Yang-Mills. We can't compute the spectrum, but we believe strongly that if we could compute it, we would get a linear ramp. We would have this linear ramp after averaging over time. I haven't talked about averaging over time, but instead of averaging over an ensemble, you can get a smooth curve by averaging over time. And we strongly believe that if you take n equals 4 super Yang-Mills, compute this quantity here, and average it over time, you'll get a linear ramp. Yes. So if you take the bulk dual of n equals 4 super Yang-Mills, you have this wormhole. And the wormhole gives the right answer. Not just that it's linear in time, it gives the right answer, including like the coefficient of this linear ramp. So that double cone wormhole is doing something right, like it's computing something right about the n equals 4 super Yang-Mills theory. In detail, it's wrong, because for n equals 4 super Yang-Mills, if you don't average over time, you should get a function that looks like this, some god-awful mess. And so what should we think about the fact that the bulk theory is giving us the right answer for an average of it? Does that mean that the bulk computation is on the right track? Or does the fact that we're not getting this complicated function here mean that we're completely off base? And I don't know.
Sorry, Douglas, may I, after Spent has done, sorry, I wanted to ask a follow-up.
Go ahead, Sandeep, I'm done.
Okay.
I'm done.
Thank you. Douglas, you mentioned in response to Shiraz's question also about the width and the scaling with n. And I'm just wondering, say for the n equals 4 theory, is there an issue of how we take the large n limit versus computing the statistics? That is, you might intuitively think that you go more towards the smoothened out ramp if you're sort of taking the n going to infinity limit. And is that how gravity works, that it sort of computes the smoothened out answer you would sort of get in the n going to infinity limit? And for any finite n, then there's a lot of structure. And that's not captured by gravity, at least if you start from the semi-classical end and try to make small corrections. Go ahead.
Well, I don't think there's any sense in which this function approaches the smooth function as n goes to infinity. So if you don't do any averaging, then it just doesn't. As n gets bigger and bigger, this function is still complicated and it doesn't approach the smooth function. So I don't think we can just say it's the large n approximation that's giving us this. It has to be the large n approximation plus some kind of coarse graining or some kind of ensemble. It's not enough just to take large n.
I see. And the coarse graining would not have to be just on time scales that went inversely proportional to 1 over n. You would have to do kind of macroscopic coarse graining just to get a sense.
You can get a pretty smooth function by coarse graining over some time scale that gets, I don't know, that like gets a little smaller as n gets large. But okay, so right, so you could imagine doing some integral over time of this function to smooth it out, and then you would say, aha, I integrated over time in the boundary theory, and I got the right answer. I got the same answer as what the bulk gave. Mm-hmm. The problem with that is that you can also compute it without integrating over time in the bulk. The bulk calculation doesn't tell you that it's integrating over time or something. You just compute it for one value of time in the bulk. Mm-hmm. And it gives you an answer that looks like it's been integrated over time.
Mm-hmm. Mm-hmm. Right. No, you should go on. I understand that the bulk answer doesn't require an integrating over time, but I was just wondering whether maybe the way it maps to the boundary answer is after the boundary answer is integrated over time, but coarse-grained only up to some order in 1 over n, and then maybe
I see.
Yeah.
So you're saying maybe, okay, good. So you say we're doing a bulk calculation, yeah, and the bulk calculation is implicitly supposed to be compared to a boundary calculation that has been averaged over time a little bit, like a small amount, 1 over n to the 1/4 power or something.
Yeah.
I think a problem with that is that even if that were true, there would still be fluctuations in this that are not correctly accounted for. But also 1 over n to the 1/4, or 1 over n is like power law, and 1 over n are effects we understand in the bulk, and it's just not being averaged over that kind of a time. We would know that.
I see. Okay.
Sorry, Douglas, can I ask? It's a very radical question to ask, but if the noise really persists at all scales, then it reminds you of quantum mechanics, actually, that in some sense, is there some other parameter like h bar actually that one may need to somehow invoke in string theory to account for this type of persistent fluctuation at large n also? I'm sorry, but
well, the parameter, it's like, yeah, the parameter that sets the scale of this noise is like e to the minus n squared. It's like e to the minus the entropy. So it is parametrically suppressed at large n. It's a very small effect. So the things we're discussing are tiny, insignificant effects.
I see.
Okay. So sorry, just one thing that's implicit in this, Douglas, my question is, isn't there, I mean, do we have a reason to believe that in the bulk that stringy effects which would appear at much before this would not contribute to this computation? I mean, why should we expect that only geometry will give us the right answer for this? I mean, why shouldn't we expect that, you know, stringy effects should be important and they could give us?
Okay. What kind of stringy effects do you have in mind? I would love it.
Well, I mean, there would be first just a spectrum, and you'd need to think of, you know, what the state of the various massive excitations is, and then there would also be, I guess, you know, just quantum gravity effects. I mean, it's not. All I'm worried about is that we shouldn't be surprised that a semi-classical geometry can't reproduce all the features. Because as you see, there are 1 over n features, and there's a 1 over lambda that appears much before that, which is.
Yeah,
much,
I mean, you're right. So we're computing something here, which is not just 1 over n, it's e to the minus n squared. So we're computing something tiny. This wormhole is like really, really small. But it gives the right answer. I mean, it gives something right, like, and it's kind of robust. Like, for example, if you study some propagating fields on this double cone, massive, like we could try to work our way up to string theory by studying massive fields. If you like, we could study a whole tower of massive fields, an infinite set of massive fields. And they really don't do anything on this geometry. They just get projected into the ground state at late times, and they don't affect this, they don't affect the...
Yeah. No, my question is more about the, I mean, maybe that wasn't what you meant to say, but I thought there's a general feeling that, you know, this suggests that a single interpretation in terms of a unitary bulk theory is inconsistent because it shouldn't reproduce all these features. I don't know if that's what you're trying to say. That's a possible suggestion. And I'm just saying that one possible way out is that, you know, the bulk theory has a lot more features more than geometry, which could help to get a lot of these.
Yes, I agree. And I agree. And that must be, I think that must be what happens in n equals 4 super Young Mills. So in the dual of n equals 4 super Young Mills, there's more stuff in the bulk, and we can't just use the wormhole. But I feel like a question in that case is, was the wormhole the right first step? Like, so you figure out all what we're missing, all these various stringy features and fuzzballs or whatever it is. And when all is said and done and we know how to compute it, do we look back and say the first term in the series was this wormhole? Or do we say the wormhole was just completely wrong? We never should have included it to begin with. And I don't know.
Okay, thanks, yeah.
Sorry, I have a question.
Yeah.
Sorry.
Go ahead.
Okay. So is it true that a particular quantum theory can have different ways of doing the ensemble average? And if so, then will each of those different ways give you different geometric dominance of the same theory of gravity, or different, like for example, Maloney-Witten does this averaging over the geometric deformation. It's almost marginal deformation. And so I'm just wondering, are there different ways of doing this ensemble average, and how should we think of these?
Well, one problem is that except in very special cases, we don't have any ensemble in mind at all. So
for example, if a theory has different, if a CFT has different kinds of marginal deformations, we can turn them on and do average over each of them.
Yes.
So that would be a non-unique way of doing ensemble average.
Yeah, I believe that ensemble average, I think that's not what's going on, because those marginal deformations are dual in the bulk to sources. So it's different than the type of ensemble that gravity wants to be described. Gravity, so in other words, those things are things we understand in the bulk. And we know when we're integrating over them, and we know when we're not integrating over them. So
I see. So even if a coupling is drawn from, even if some set of couplings are drawn from some random ensembles, even then can one not define different ways of doing the ensemble average?
I mean, I'd settle for any way of doing an ensemble average. I don't know.
And will then the gravity theory be always the same gravity theory?
Well, probably not. Like, for one example of that is well, there are slightly different ensembles that are dual to slightly different two-dimensional theories of gravity. So one case where this is worked out in some detail is some simple theories of two-dimensional dilaton gravity. And there's slightly different ensembles that are dual to slightly different theories of gravity.
I see. And in some sense, taking some asymptotic limit of some parameter, does it also induce some kind of averaging? Like for example, when we derive the Cardy formula, we take this large limit of something, or some conformal dimension, it induces some averaging, right? Like ETH is also in some sense.
Well, but the Cardy formula, I mean, it tells you about an integral over the density of states. So it sort of does the averaging by integrating over all the energies.
But naively taking this large energy limit does a sort of a...
Well, you argue there that at large energies, the spectrum is kind of dense, and so it can be approximated by continuum.
Right, so it kind of coarse grains automatically.
Yeah, but here there's no, I think that would be sort of similar to like taking a time average here, but we're not taking a time average.
I see.
So, well, we got a bit off track here, but the puzzle, so just to review this sort of mini part of the talk, the puzzle was these wormholes break factorization, and they seem to be need to interpret them in terms of an ensemble. That means wormholes are bad, but there's these wormholes that actually compute something that looks right, like they compute a type of average of the actual quantum noise that we think is there in a particular theory. And what are we supposed to make of that? And
yes.
A temporary conclusion is that it looks like gravity is describing some kind of average over quantum theories. It doesn't mean that all theories of quantum gravity and string theory are dual to ensembles. It definitely doesn't mean that. Like the dual of n equals 4 super Mills is not dual to an ensemble, just tautologically. And so there must be a way that string theory can produce this curve here and not this curve here. But I don't think that gravity does that. I think it, is more, it goes beyond geometry somehow. Okay. So now we can come to the question that we want to address in the talk, which is, are the replica wormholes for the page curve describing quantum noise like this? And do they need an ensemble interpretation? So does the wormhole computation we're doing with gravity require an ensemble interpretation in the same way that the double cone wormhole requires an ensemble interpretation? Okay, so let's discuss a case where replica wormholes are relevant. So this slide's going to be a little bit annoying. It's like a bit of setup for the case we're going to describe. Sort of fixing the notation of the pictures. So let's take a state psi. It's a combined state of a black hole system and a bath. So the black hole system is interacting with the bath. And the black hole starts out as it actually has two subsystems. It's an entangled, it's like a two-sided black hole. It's starts out in a thermal field double state. That's what this semicircular arc represents. It represents the Euclidean evolution that prepares the thermal field double state. And the bath starts out the same way. And then this vertical segment here corresponds to real-time evolution. So the circular parts are Euclidean evolution preparing the thermal state. And then the vertical parts are real-time evolution. So we're evolving the system forward in real time. And the red lines indicate that there are interactions between the right side of the black hole, so one of the two black hole systems, and the bath. So this picture with time contours looks a little weird, but if you want to have a picture with geometry that's shown on the right, this is the kind of geometrical setup. We have a two-sided black hole here. This gray region is the Euclidean state preparation. And then we're evolving it forward on the right side and letting the black hole interact with a bath. So this is the setup, basically the setup that was considered in the papers that I mentioned earlier. Pennington, Almhiri, Engelhardt, Marolf, and Maxfield considered things similar to this. So we want to compute the page curve. That's an entropy, trace minus trace rho log rho. We'll compute something a little bit simpler, which is the Renyi entropy. That's trace of rho squared. And let's compute the trace. Well, it doesn't matter whether it's the trace of rho squared of the bath or of the black hole. I should have done this for the bath, but actually the notation I used here was for the black hole. So trace of rho squared for the black hole means the entropy, Renyi entropy of the two dots, the subsystem described by the two dots. So we take a black hole, we let it interact with the bath, and then we compute the entropy of either just the black hole or just the bath. And that's supposed to grow with time as the two systems become entangled with each other, but it's not supposed to grow forever. That's the basic page curve in this case. So the time contour for computing the Renyi entropy, trace rho squared, is this more complicated diagram here. It has 4 separate components. 2 of them are the black hole and 2 of them are the bath. And if you look at the bottom left corner of this diagram here, then that's just a redrawing of what we have in the top left. So in particular, the circular arcs represent Euclidean evolution, and the straight lines are real-time evolution. So this is forwards in time and then backwards in time. And the red lines are interactions. Okay, so that's the time contours for computing the Renyi entropy. And ADS-CFT says we're supposed to fill those time contours in with some kind of geometry. And at late times, the interesting way of filling in the geometry is this wormhole here. It's a wormhole with like a cylindrical topology connecting the 2 black hole time contours. The black hole time contours are topologically a circle. And so we have 2 of these circles that can become connected by something with the topology of a cylinder. So that's this thing that's called a replica wormhole, and it's the underlying geometry behind the computation of the page curve. So we have a wormhole here, and these 2 replicas of the black hole are connected. So do we have a problem with the factorization? And okay, actually we don't in this case, because the boundaries that we're studying, the boundary conditions, are themselves connected. They're connected together by these interactions. So there's no obvious contradiction, like this thing fails to be the square of something else, because it's not supposed to be the square of something else. It has all these interactions coupling the systems together, and it's sort of an irreducible computation by itself. It isn't supposed to factorize into anything, so there's no problem with there being a wormhole. So that's the 0th order answer to the question, is that there's no problem. Okay, but now let's try to understand where this answer comes from. So let's try to understand the density matrix of the Hawking radiation. So rather than just computing its entropy, let's try to compute the density matrix. This was the thing on the first slide. I claimed that the density matrix has to be a complicated thing. So gravity is going to have trouble describing the density matrix. Okay, so how do we compute the density matrix of the radiation? So at late times, this time evolving black hole, the state of it looks something like this. We have different possible sequences of Hawking radiation of the black hole. And the Hawking radiation gets captured into some radiation system R. So I here labels a different possible sequence of Hawking emission events. So first you radiate a photon in this direction, and then a graviton in that direction, and then an electron in this direction, and so on. So I is a sequence that describes a particular history of Hawking radiation, and we're summing over all possible sequences, and we have a tensor product of the state of that stuff in the radiation. And then the other factor is the black hole in whatever state is left over after we've radiated that sequence. So psi I is the state of a black hole that has emitted Hawking radiation in sequence I. That's what's written here. Psi I is the state of the black hole that's left behind after you've radiated a particular sequence of Hawking quanta. Okay. And K is a normalization factor related to the number of different sequences. So the density matrix of the Hawking radiation, if we just compute the partial trace of this with this state, the matrix elements of the density matrix of the Hawking radiation rho R are given by inner products of these states psi I and psi j. So the matrix elements of the density matrix are inner products of states of the black hole with different radiation histories. So the words here are kind of awkward, but hopefully the point is clear. To compute the matrix element of the density matrix, you need to compute an inner product of different states of the black hole that correspond to different Hawking radiation histories. So let's try to draw a time contour to compute that thing here, this inner product. Well, we have the thermal Euclidean state preparation of the black hole. This circle is still there. And then we evolve the black hole forwards in time and backwards in time, and we insert operators that collect a particular sequence of Hawking quanta. So these operators are, if you like, you could imagine these operators are like annihilation operators for a particular sequence of Hawking quanta. We've forced the black hole to first radiate this particle, and then that particle, and then this particle, and so on. And that time contour here computes the inner product of these two states. So one state corresponds to a history of Hawking radiation labeled by these V operators, and another state corresponds to a history of Hawking radiation labeled by the W operators. So that's the type of inner product that we need to compute in order to compute the density matrix of the Hawking radiation. And on later slides, I'm going to refer to this just as the inner product of state W with state V. So W and V correspond to two different histories of Hawking radiation. So in Hawking's calculation, this quantity, this inner product here, would be basically, essentially diagonal. But to get the right answer for the page curve, there must be off-diagonal entries with typical size e to the minus s over 2. So this is related to this comment that Hawking's calculation can give a simple answer for the density matrix. That would just say be like a multiple of the identity matrix, basically. But in order to get a density matrix that satisfies Page's curve, it has to be a complicated matrix with piles of off-diagonal entries that are very small, huge number of tiny off-diagonal entries. So it has to be a very complicated matrix. So somehow the inner product of these things has to be complicated. Okay. Now we can just try to compute these inner products in the gravity theory. So if we compute the inner product of W with V, then we just start with this time contour here, and we need to fill it in some way.
I had a question.
Yeah.
In the previous slide, what is psi I B?
Psi I is the, you're referring to this part here?
Yes, yes.
Yeah, so psi I sub B is a state of the black hole.
But what does it mean to take a product and then sum over all the states of a black hole?
Well, it's not all the states of the black hole. We're summing over possible states of the Hawking radiation. So let's say this state describes the black hole after it's emitted 100 Hawking quanta. So the total state of the system will be a sum over the states of those 100 Hawking quanta, tensor product with whatever state of the black hole is left over after you've emitted that particular set of Hawking quanta.
this sum covers both of the terms of the product.
Yes. It's the sum, it's one sum. The index I is the same in both cases. That represents the fact that the black hole is entangled with the radiation. It's like if the black hole emits particle 1
like
or
the
particle
state of black hole at multiple times.
Sorry?
This is like summing over the state of black holes at multiple times, right? I mean, because
No, it's the same time. It's just that the different terms in the sum correspond to different ways that the black hole could have emitted Hawking radiation.
okay.
Like suppose you go out, let's try to think about it physically. Like you have a black hole that's emitted a bunch of Hawking radiation. And suppose you just measure the Hawking radiation. So 100 photons or whatever have come out, and you measure all 100 of them. And you find the polarizations of the different Hawking quanta. There's some leftover state of the black hole. So you get an answer for a list of polarizations, and after you get that answer, there's some state of the black hole that's left. If you had done the measurement and found a different sequence of polarizations, then there would be a different state of the black hole. And for each sequence of polarizations that you measure, there will be some different state of the black hole.
Thanks.
Yeah. So it's the inner product of those states of the black hole are what determine the density matrix of the Hawking radiation. So here we're trying to compute the inner products of those states. So here's the black hole where it emits a particular sequence of Hawking radiation, like photons with particular polarizations. And here it is emitting photons with different polarizations.
Douglas, can I ask a question?
Mm-hmm.
Hi, Douglas.
Hi.
So in this sum, you're assuming that some kind of Gram-Schmidt has been done, so that the amplitudes are all 1, and there is a single index I. I mean, to begin with, you would have some kind of Cij, IR, psi JB, that kind of stuff. And then,
yes.
So therefore, and you can.
Yeah, I'm not. So that would be you would get that Cij kind of thing if you were expanding this in a basis, an orthogonal basis for the radiation and the black hole, some basis you'd chosen in advance. Here, I'm only choosing the radiation basis, and the black hole states are just whatever you get.
Yeah, so they're not orthonormal.
No, they're not, and that's important that they're not orthogonal.
Right.
Yeah, in fact, right. What you said is also true. It's not only just that they're not orthogonal; they're also not orthonormal. So they're not even normalized the same way. So they're just some unnormalized states of the black hole. But you can always write it this way. The coefficient I wrote out front is a little bit sloppy, but I was trying to simplify things a little bit for this slide.
Yeah, so this K here is the dimensionality of the number of I's. So the
yes.
Right.
Roughly, I mean, a more precise formula. We could try to write a more precise formula, but I don't think it's too important for this.
Right. Okay. Thank you.
I mean, this formula could be literally true, depending on how we define the states I. But right, so Hawking's answer is basically that so I said that these states are not orthogonal, but in Hawking's calculation, it actually ends up that they are basically orthogonal. So the black hole states corresponding to different histories of Hawking radiation are basically orthogonal to each other. The reason for that is that they're the interior partners of the Hawking modes, and those will be in different states. for different histories of Hawking radiation. So you'll get an orthogonal state. That isn't too important, but the main point is that this inner product is basically just Kronecker delta in Hawking's calculation. But if we take two copies of the same inner product, then we can have the same contribution, two copies of Hawking's calculation, that gives Kronecker delta again. But we can also have a wormhole connecting together the two boundaries. And I'll show you a little bit more about this wormhole, but it gives a contribution that's e to the minus s. And it basically doesn't depend on W and V. So even if W and V, these two histories, are completely different from each other, this thing will be non-zero and will give an answer that's small, but not insignificant. So this e to the minus s term that we get here is consistent with the page curve. So this is kind of the difference between Hawking's calculation and Page's calculation, or the page curve. And this e to the minus s term basically, well, it comes from the same place as this wormhole that gave the page curve for the Renyi entropy. It's kind of the same wormhole. So it's not surprising that the e to the minus s we get from this wormhole sort of fixes the entropy and gives us the things that are consistent with the page curve. But now we do have a problem with factorization because these two answers are not consistent with each other. And that's just the same inconsistency that we found a few slides ago. It's because this wormhole is contributing to a quantity that was supposed to factorize. So,
hello?
Yep.
So say we just have like one V and one W.
Yeah.
So then it is, so is this the same calculation as you know, like what you and collaborators did for this OTOC calculation where you have the VW?
It's different because there's two different boundaries here. The OTOCs there are 4-point functions on a single boundary. And here we have two disconnected boundaries. So it's completely different quantity from OTOCs.
Okay, so in that computation, is there a wormhole, or is wormhole important for getting the maximal chaos? Or
no, it's not. It's not.
Okay, so sorry, what was the? So there are no wormholes, or?
There are no. Okay. Actually, if you look at basically there are no wormholes, but if you do look at the OTOC at extremely late times, then I think the dominant contribution does come from a space that, it's a single boundary, but it has a wormhole. It's a space, it would be a space that looks a little bit like this one here. It would be this kind of thing, would give the OTOC at extremely late times. Basically, yeah.
But it's extremely late. I mean, I wanted to know whether the maximal, you know, the chaos exponent itself.
No, it has nothing to do with that. Absolutely nothing to do with the chaos exponent. No.
Because that is suppressed in 1/n, right? It's not suppressed e to the power minus s.
Right. It's yeah, exactly. That's a perturbative gravitational interaction. It's not a wormhole. It's completely unrelated.
Okay.
Yeah.
So when you mean long times, you mean much longer?
Yeah, I mean like exponentially long times.
Okay.
E to the s times.
Okay.
Yeah.
And is this late time inducing some sort of averaging, or taking this?
I think so. I think that late times is causing you to focus on this quantum noise, and gravity doesn't describe quantum noise, but it does describe an ensemble average of quantum noise. So that's the connection between late times and wormholes.
So in some, if we know the result from a CFT calculation, exact result for the 4-point function, then one should be able to see this contribution from the OTOC.
Yeah, but we never know an exact result for this kind of 4-point function for the OTOC in a CFT.
So for some specific model, maybe like a Liouville CFT.
Oh, Liouville. Well, okay. Let's study something with. Let's study something with a discrete spectrum, so it has this quantum noise. Then you never get an exact formula, because the exact formula would have to do this or something like this, and
That we don't know any example.
Yeah, it's not just that we don't know them. Like it's not really reasonable to expect to be able to produce a function that would give random kind of behavior like that. So it's not really, yeah, it's not really our fault. It's just those things are too complicated.
Yeah.
Okay, so this computation here of the density matrix is using the same wormhole as for the Renyi entropy, but now it requires an ensemble interpretation. So this is kind of what I claimed at the beginning, that gravity is too simple to describe the actual complicated density matrix, but it sort of cheats when you go and try to ask it about the density matrix, not just the entropy, but actually about the density matrix, then it gives you the answer for an ensemble. So it's a type of cheating. Okay, so now let's try to discuss this wormhole in a little bit more detail. So we'll come close to the situation that was just discussed with just two W and two V operators. This is the simplest case where we can discuss this wormhole. Rather than having a whole sequence of these things, we'll just have two of them, and I'll arrange them like they're arranged here in a kind of a symmetrical way to make the solution a little simpler. And we're looking for a solution with a topology of a cylinder connecting these two topological circles together. So let me show you how to construct the solution. It goes in steps. So this circle here, this big circle, is the Poincare disk, the two-dimensional hyperbolic space. So we're going to be working in JT gravity, two-dimensional gravity. So this circle is the Poincare disk, and this is just a horizontal line that we drew through it for fun. And then there's a smaller circle inside the Poincare disk. Okay, so that's what this drawing is here. So we're going to go through a sequence of steps to construct the solution. The first step is to take this smaller circle and translate it to the right in the hyperbolic plane. The next step is to translate it vertically. So now we've translated it over and then up. And if you plot what happens to this horizontal line here, nothing happens to it in the first stage, and then it gets moved upwards and deformed in this way. So we end up with this thing here, been translated in these two directions. Then we repeat this same steps with another circle, but with the opposite translations. So we end up with this diagram here. Now, if you take this diagram here and just focus on the shaded region, the region inside these circles and inside the horizontal lines, you get some shaded region here. And now we take two copies of this thing. So just take two of these and glue them together along the horizontal lines. That makes something with the topology of a cylinder, and it looks sort of like this picture I drew on the right here. And that's basically what the solution looks like. At these corners, the corners are where the operators, V operators and W operators, are inserted. So I don't know how clear it is from the picture, but if you look at the boundary of the gray region, that's supposed to be the time contour. The two time contours are supposed to be the boundaries of the gray region. Each one has one W and one V operator in it. And the geometry of the time contour, as drawn, it doesn't really look like what we wanted. In particular, it doesn't have any real-time component. But so what you're actually supposed to do is you're supposed to take this geometry here and analytically continue this translation parameter X. You analytically continue that to imaginary values. And that gives the actual geometry that you want. So it's a wormhole. It's a complex wormhole. So complex meaning not real, not pure imaginary. It's a complex geometry. And this is how you construct it in JT gravity. So in the microcanonical ensemble, it's a classical solution. And we can kind of describe aspects of it by giving the distances between some points. So here I drew the time contours again with the V and W operators, and I drew 3 extra dots, these black circles. And we can discuss how far apart these points are through the bulk, through the wormhole. It turns out that points 1 and 2 are close together. They sort of feel like they're on the opposite sides of a thermofield double. And that's this function here. If T1 is approximately equal to T2, then this is small. Or it's not large anyhow. Points 1 and 3 are far apart. And they sort of feel like they're on the opposite sides of an OTOC timefold. So that's where something like OTOC physics gets involved, although we're not computing an OTOC. We're computing something else, but OTOC physics still gets involved. And the distance between those 2 points is this simple form. So it has a term that is small if the times are equal to each other, but then it has another term that's big, even if the times are equal, as long as the times are fairly large. So if we're far away from the end point of the contour, then the time parameters T1 and T3 will be large, and this term will be big. So the distance between these 2 points is large. So that's qualitatively what it looks like. It's a wormhole where these 2 points are close together, and these 2 points here are far apart. Okay.
Sorry, I have probably elementary confusion. If you didn't have your time contours, your wormhole would just be this trumpet. Now, the time contours seem to me to emerge from the sort of the edges of the trumpet, whereas in your diagram, the edges seemed unchanged, but everything was happening in the bulk. I couldn't understand that.
Which diagram? Shiraz, which diagram are you referring to?
The diagram with the gray regions, the ones in the previous transparency.
Okay. This one?
Yes.
Okay.
Are those, yeah. Why aren't the time contours reaching the edges of the contour? Why aren't the funny things reaching the ends of the trumpet?
Oh, I see what you mean. You mean these boundaries way out here?
Yes.
So the asymptotic boundary that's associated to the quantum system, the ADS boundary, has been regulated to finite radius, and it's the boundary of the gray region. We should take it to be large, and what that means is that we should take this small circle here to be a very big circle. And I just drew it this way to make it a little clearer, but I can see in retrospect it wasn't very clear. This line here should be asymptotically close to the big boundary.
Thank you.
Could you also say what T1x and T2y mean?
So T1 of x is a translation operator, it's an isometry of the hyperbolic plane that moves things to the right. And T2 is something that moves things vertically so 1 and 2 correspond to the horizontal and vertical directions. And x and y are the parameters, how far you've moved. So here we move by distance x, and here we move by distance y. And to construct the actual solution, we want to take x to be imaginary. So then we're no longer looking at a piece of hyperbolic space, we're looking at a piece of complexified hyperbolic space.
So you're saying to get the boundary dual, which looks like the two contours with extended time and real time and so on, you have to do this in the Euclidean geometry? Or,
yeah, so to get one like this, you need to take that x parameter to be imaginary.
Okay.
Sorry, Douglas, if I may ask a question, is that okay?
Yeah, please.
Yeah, so I'm sorry, I followed the construction rather poorly, especially the transparency after this. But just to understand, are these saddle points or are they configurations? Because the double trumpet is not actually a saddle point in JT, right?
Yes.
So what about these complexified wormholes?
So these ones they're saddle points in the microcanonical ensemble.
I see. So you work not at fixed temperature, is it? At fixed energy?
That's right. Yes, fixed energy instead of fixed temperature.
I see. So, and you're still doing Euclidean, if I understand, right? This is Euclidean. Oh, this is complexified hyperbolic space with the boundaries being Euclidean. Is that correct?
Well, the boundary has both the Euclidean component, that's the circle here, and the Lorentzian component.
Okay, and the Lorentzian. I see. Okay, and then, sorry, you said these are honest to goodness saddle points, if I understand.
Yes, actually, we can explain why there's saddle points and whereas the double trumpet was not. So the saddle point condition, in order for the geometry to be on shell, the boundary has to be made of circular arcs. So that's what an on-shell geometry looks like. It's one where the boundary is circular arcs. And you can see here that the whole thing is made up out of circular arcs. It has cusps, and the cusps are where the operators are inserted. So it wouldn't have been a solution without the operators being inserted, but it is a solution with the operators inserted. And if you remove those cusps, there's just no way to build something like this where the boundary is made up of circular arcs. It's because we've inserted these operators here that we can have a solution. And it's a reasonable solution in the microcanonical ensemble.
And how much information about the exact nature of the operators did you need? Did you just need some kind of a deficit angle or something they create, or do you need actually that you're working?
You need to know the conformal dimension. And the classical analysis is reliable if the conformal dimension is large compared to 1. But we can do another computation that's valid for any value.
Okay, thank you.
And Douglas, how to understand this factor of G Newton, relative factor of G Newton?
Yeah, so it's because this piece here is a back reaction effect associated to the insertion of this W operator. So if this operator was not inserted, then points 1 and 3 would be close together. You just go forwards in time and backwards in time, and you end up in the same place you started. So if there's no W insertion, then points 1 and 3 will be very close to each other. But if we insert the W operator, then you go forwards in time, and then you get a little kick from the W operator. The kick is suppressed by the gravitational coupling G Newton, but it's enhanced by time evolution. And it's that interplay between chaos and this exponential growth in time and small G Newton factors that makes this solution possible.
Okay.
Otherwise, you would be suspicious, like, how can inserting just a couple of operators make an on-shell solution possible here when it wasn't possible for the double trumpet? It's because inserting those operators actually makes a big difference, because they lead to this kind of exponential growth.
So Douglas, just to confirm, so this is the same kind of exponential growth like in what happens in the OTOC calculation?
Yes, it's the same.
Not the OTOC calculation, but it's similar.
And if you look at it, let's just set T1 equals T3, then the growth with time is e to the 2 pi over beta times T.
Right. Yeah.
And it's the same thing that happens in an OTOC, where 2 points on opposite sides of a time fold like this get far away from each other. That's the basic physics of the OTOC is exactly that. So this solution here is kind of a combination of OTOC physics and the thermal field double. Okay, so I'm almost finished. Let me so that was enough of the classical solution. What I want to do next is show you a exact calculation, a quantum calculation in JT gravity of this thing, and show that it lines up exactly with a ensemble average. But first I want to show you what ensemble average we're talking about. What, not what the ensemble is exactly, but what type of thing the quantum calculation will line up with exactly. So let's continue looking at just this simple case with two W and two V operators inserted. And we'll call that quantity F. If I take that and write it out in terms of matrix elements of these operators, so I and J are different from the I and J that we had before. What they mean now is just energy eigenstates of the boundary quantum mechanics system. So if you take this quantity here and write it out in terms of the energy eigenbasis, you get these V, W, and V operators, you get some time evolution, and if you write out both factors, you get this expression here. So it has some matrix elements of the W operators, the V operators, and okay, I'm complex conjugating one of these factors. And then it has some phases from time evolution and some suppression factors from the Euclidean parts of the contour. So let's just evaluate this quantity using the following rule. We don't know what these matrix elements of the operators are. Those are complicated. Those are like this kind of quantum noise information. They're hard to know exactly. But let's just make up an ensemble. And let's say that in this ensemble, the average value of this matrix element is 0. And the average of a product of two of these matrix elements is diagonal in the I index and in the J index. So basically, the matrix element has 0 average, but its square has some non-zero average. And we'll parameterize that by this function on the right-hand side with this funny notation. So this thing on the right-hand side is just some function of energy. So here we're just making an ensemble where we say that the expectation value of the matrix element is 0, but it has some variance. Okay, so if we take that formula and we plug it into this expression here, and we take the ensemble average, then we get the following expression. The sum over ij and kl reduces to just a sum over I and j because of these Kronecker deltas. And we get a simple expression in terms of the W and V functions, the variances of these matrix elements. So if we like, we can write that as an integral over energies with a density of states with these functions of energy. And okay, what should we take for this function of energy, this function WEE prime? We can determine this by matching to the 2-point function of W operators. And if you take the 2-point function in JT gravity, then this expression here has a simple expression in terms of gamma functions. So that's a prediction for what the answer for this should be in an ensemble where we average over the precise values of the matrix elements, but we keep track of the variance of those things. So the matrix elements are complicated. These operators are complicated matrices, but we make an ensemble where we have simple formula just for the variance of the matrix element. And we can determine that variance by matching the 2-point function, and then we make a prediction for this quantity F. Okay, the prediction looks like that. And you get exactly that answer from the exact calculation in JT gravity.
Douglas, can I ask you a question?
Yeah.
Yeah, so if you go back to the previous slide, yeah, so some of this technology is similar to ETH.
Yes.
And where there are a number of things that you have to assume about the operators. For example, these W and V operators should be like, few body operators involving only some few sites kind of thing, and also about nothing about long times, but I'm saying that the operators W and V, do you have something specific about them in mind?
Well, yeah, in this case, I do have in mind that they're few site simple operators. Like they would be like photon creation and annihilation operators or something in the black hole picture. So there's some kind of simple operators. So that's one part of the answer. Second, though, I think ETH actually applies to complicated operators, but let me comment on how this is different from ETH.
Mm-hmm.
In ETH, there's no ensemble. So you kind of manufacture an ensemble by averaging over the I and J variables.
Yes.
Here, we're doing something slightly different. Here, we're making up an ensemble, and we're not averaging over I and J. We're saying that in some ensemble of systems, this is true.
But
the difference
saying that if you actually did this sum over IJKL, I mean, it's sort of, yeah, so like the off diagonal, yeah, the first statement that the average of Wij is 0, it is sort of like the ETH statement that the off diagonals are down, by some e to the power minus s or e to the power minus s by 2 kind of thing. On the other hand, in the second one, yeah, so these two statements.
The first statement is like saying that in ETH, you have some random phases, and the first statement is kind of like saying the average of those random phases is 0, but the variance is
random. Yes. I forgot. It's not about the how
the difference is that this quantity that we're computing here is not self-averaging. So you don't, if you try to compute this in a particular quantum system, you don't get to use ETH formulas. You only get to use ETH formulas if there's an ensemble. So if we computed this F for a particular quantum system, we wouldn't be able to use ETH to compute it. It would be some quantity that would vary erratically depending on which operators we chose, and it would vary from one quantum system to the next. It contains, F is pure quantum noise. And it doesn't, right, so in order to apply these types of formulas, these types of simple formulas, you have to actually take an ensemble average. It's not enough to just say, look, we're summing over I and J in this formula, so we can use averaged quantities. You have to actually take an ensemble in order to get this, in order to compute this F.
I see, because this IJKL go over the entire Hilbert space rather than a particular energy band. Is that the?
You're asking why it's not self-averaging.
Why can't I use the ETH assumption to each of these matrix elements?
Oh, it's because, so let's see, when can you apply ETH? You can apply it, one case you can apply it is if you're summing over I and J, let's say, of some kind of positive quantity. Here, you're summing something that's not positive. So
I see.
It ends up being dominated by the fluctuations. It's not something where like, that has a nice average value.
I see. It's not like A dagger A. It's each of these things are like A. I see, got it. Is that the difference?
I'm not sure what you meant by A dagger A.
I mean, each of these things, I mean, the energy, for example, would yeah, so if W and V, these things were like, is it because they're like annihilation operators that I cannot use the ETH assumption? Why exactly can I not use the ETH assumption? Because they're in something like in momentum space kind of thing, or what?
It's because the quantity is not, so let's, I think it will be simpler to think about if we just consider one of these. So F is a product of two factors. Let's just look at one of them.
Right.
And that one is just the sum over I and j of these this first term here. So ignore the terms with bars over them, just the first terms.
Yes.
And let's see if we can apply ETH to that. So if we had a W here and a W here, then we would be able to apply ETH to it. This would be some kind of 2-point function. And it would be a sum of positive quantities. And we could use ETH to compute it. But with a W here and a V here, if those operators have a small 2-point function, then these things are basically uncorrelated with each other. And the sum over I and j is a fluctuating sum of positive and negative quantities, more generally complex quantities. And it just doesn't average out. It's like adding up a bunch of random numbers. The result is still some kind of random positive and negative numbers. The result is still something that's that fluctuates.
So you can't get the exact
is
number,
it true?
estimate its magnitude, right? I mean, just from the fact that you have n random numbers and the answer should be root n.
Well, the average of the answer should be root n. But the answer itself will still be Gaussian. It will still have it will have order 1 fluctuations. Like it will have the fluctuations in F will be as big as F is itself. So it's not self-averaging. It's really similar to taking, yeah.
Wij looks very much like a random matrix problem, right? I mean, as Wij, the matrix element is an element of a random matrix ensemble.
Yes.
Yeah,
here we're picking some simple ensemble for it, but
right.
Yeah.
So Douglas, I agree that means you can't apply naively the Wij answers for ETH, but something which like Srednicki did to prove this OTOC from this extended ETH. So there was an answer for Wij Vji for this entire matrix, for this product of these two matrix elements. Can some answers like that still work out?
Was that for a case where those operators had a non-zero 2-point function?
I think so, yes.
In the case where they have a non-zero 2-point function, then there would be an ETH way of computing this, and it would be a sum of basically positive quantities. But
you still need to extend the ordinary ETH to this to this product of these matrix elements to a bigger, means to a higher moment of the statistics.
Oh.
So not just the second moment, but the fourth moment of the.
Oh, you mean to compute, since we have 4 matrix elements here?
Yes.
Yeah, I think it's, well, here I'm assuming basically they're Gaussian. I mean, so in the bulk theory, it ends up being that these are approximately Gaussian, at least at late time. So the higher moments are not interesting. But in general, you could imagine that there would be non-zero higher moments.
Right, means could one frame a ETH like answers using those higher moments to calculate this?
No. Not if W and V have a small 2-point function. Then it's really just, then F is not self-averaging, and there's no way of applying ETH to compute this. You have to invoke an ensemble.
This is, I think, also the subject of the paper by, maybe Srednicki makes this assumption. I'm not sure.
So shouldn't I be drawing from the ensemble after I sum over the full full F, like after I calculate the whole F? Why am I? Why can I substitute for these ensemble averages in between?
Oh, here, well, I'm not, yes, we should compute the full ensemble average of F. And basically what I did to get this formula here is assume that these things are Gaussian with this variance and a similar formula for V. So we just have a weight contraction between the two W terms and between the two V terms. And that gives us this expression.
Okay, and you assume W and V are uncorrelated. Maybe
Yes, yes. I didn't write that here, but that's an important part of this assumption. W and V are uncorrelated. You could also consider cases where W and V are correlated. It sounds at this point like I'm making a whole bunch of arbitrary choices.
Right.
But these are the choices that define a certain ensemble, and it exactly agrees with the gravity calculation. We could soup up the gravity calculation so that W and V would have correlations, but it's not necessary. The simplest case is this one. Okay, so let me just, I think this is my last slide with content on it. So let me just explain it briefly. Well, maybe I don't need to explain it. It's this is just a JT gravity calculation of a quantum JT gravity calculation of this wormhole that we did a classical calculation for before. And the main message is that it's easy and you can compute it. It's actually a lot easier than the classical calculation. And it gives exactly this formula here when you put in the gamma functions for these 2-point functions. So
sorry, Douglas, if you're going to go over that very quickly, I do want to ask you, what exactly do you mean by saying it's quantum? Do you mean it's beyond semi-classical and an exact result in JT?
Yeah, so for example, you don't need to take the operator dimensions to be large. It's an exact calculation using of JT gravity on this topology.
I see. So you mean all the determinants and so on, if you think about it as some saddle and corrections, they've all been summed exactly here?
Yeah, and the fluctuations in the boundary mode and the Schwarzian theory and all that stuff has been computed exactly.
Isn't that really impressive? I mean, I don't know. I see.
Yeah, well, it's this, I think it's really beautiful, but it's this formalism, this exact quantization of JT gravity. Kitaev, Su, Jinping Yang, and Phil Sod worked this out. And it's really beautiful, and it's extremely easy. Basically, you just glue together, geometries out of simple building blocks. And for this computation, the only building block you need is this rectangle. And the rectangle has some expression. It's like moderately complicated. It has a couple of Bessel functions in it. But these Bessel functions are themselves nice functions. They have some orthogonality properties, and it allows you to write a simple expression for this integral. So to make this wormhole, you just take two rectangles, a blue rectangle and a green rectangle, and you glue them together. And gluing them together just means multiplying these things together and integrating over L. So it's really very simple calculation.
And then the matter is only introduced insofar as the deficit angles generated due to conformal dimensions or something, or
yeah, the matter is included by including the quantum 2-point function of the matter of the inserted operators, these W operators. And that means that you should weight this configuration by each of the minus the length between those points. So these are these red factors here. That's the contribution of the matter. So
at least for heavy anomalous dimensions, I guess.
No, this is valid even if the anomalous dimensions are small. Because, well, okay, you've got me a little bit. I lied a little, because on this cylindrical topology, you can also have a geodesic that winds around it, but that contribution is unimportant at late time. It's exponentially small. But up to that, the geodesic contribution is exact. That's a property of the ADS2 propagator, of the wave equation.
I see. Very impressive. I see. Okay. Go ahead.
So this calculation precisely matches with this ensemble. So well, so I tried to argue here that this wormhole here, it gives this e to the minus s answer, which is what we need. And in the next slides that we just discussed, I was showing that the detailed form of the e to the minus s answer agrees with this ensemble average using a simple definition of an ensemble. It precisely matches what you would expect. So again, it's a case where you're forced to invoke some kind of ensemble. You say that gravity is computing some kind of ensemble average. And in this case, it's like it matches the ensemble expectations very precisely.
I see.
Okay, so let's come back to this question.
I think, sorry to keep interrupting. I think Shiraz is waiting to ask you something, but I do have a follow-up, if you'll permit, to what you just said after that. Let me hold on. Go ahead, Shiraz.
I'm good. I'll wait till the end.
Okay, so Douglas, just to ask it, but then you can come back to it later on. The exact calculation you just had and so on, with matter, does it, I'm just wanting to confirm something which you probably already said, but you know, if one looks at the double trumpet geometry with matter, there is an issue that perhaps the blowing up Casimir energy at the neck of the double trumpet might actually cause the two to disconnect. Could have been. At least wasn't clear to me, and in fact we were setting up to do those kinds of calculations. But you say now with all this, it's clear that those configurations do contribute even with matter. Is it the back reaction controls it, or?
No, this is an important point. Okay, so let me explain. Let me recapitulate your question and then try to answer it.
Okay.
So here I said that the only effect of the matter was inserting these factors. But in addition, we should also do a one-loop determinant of the matter fields on this geometry. So not just the operator insertions, we should also compute the path integral of the matter field, so a determinant. And I've just set that determinant equal to 1 in this calculation. That is correct if the wormhole that is relevant is big. And at late times, it's big. It's proportional to time. But so at late times, it's an excellent approximation. But there's still a part of the moduli space when you integrate over this moduli of this cylinder where the cylinder is small. So the classical solution, the cylinder is very big. But if you do the full integral over the moduli space, then there's a region where it's small. And in fact, that region is divergent as you anticipated. So the calculation I'm doing here is not fully consistent. It's some kind of quantum calculation that captures all of the fluctuations around the classical solution, which corresponds to a big wormhole. But I'm throwing out a far away region of moduli space where the calculation would actually diverge. I'm assuming that the gravity theory somehow cures that infinity, and then the calculation would be correct.
I see. Okay, maybe offline I'll chat with you a little bit as we try to do this calculation a little more to get your comments.
Okay, yeah, sure.
Okay, thank you. Yeah, go ahead, Shiraz.
No, I'm good. I'll just wait till the end of the talk.
Okay, well, the end is near, so this is the last slide. So I'm just returning to this question: do the replica wormholes with page curve need an ensemble interpretation? And we saw halfway through the talk that if you treat them if you treat that calculation as a black box, then they do not. They do not need an ensemble interpretation because the wormholes that are involved connect together systems that were coupled to each other. So there's no contradiction with factorization. But you can ask about the matrix elements of the density matrix that gives this entropy. So we can go beyond just the entropy and we can ask about the density matrix itself. And when we compute that, the simple gravity computation seems to require an ensemble by an ensemble average, require an interpretation by an ensemble average. because we have this funny situation where this thing equals 0. I left off the equals 0, but I should have written this equals 0, but the square of it is e to the minus s. So I feel like just the question I'll end with is the following. In cases where there's no ensemble, like in the boundary dual to n equals 4 super Yang-Mills, we're sort of left wondering, are the replica wormholes the first term in some computation that can be systematically improved? Or are they not? And if they are, then what is the next term? Okay, thank you. That's the end of my talk.
Oh, great. Thank you very much, Douglas, for the very nice talk. So maybe we can unmute our microphone and clap up. Right. That's the question. So if you have any question, please go ahead.
I have a question.
Sorry, Suraj, go ahead.
Yeah, Douglas, it's a vague question, but it's related to something I asked earlier in the talk. Sometimes it might happen that if you look at complicated enough correlators, you might have some Bell inequality kinds of relations that might preclude a classical ensemble interpretation. I mean, it's a vague question, but is there any sense in which one could investigate such kind of consistency conditions here?
Oh.
If you look at correlators of operators that don't commute, sometimes you might have Bell inequalities, and they might, you might have. In particular, in the diagram you showed at the beginning, the question would be, you could try and compute like with maybe more boundaries correlation functions, and then ask for Bell inequalities in them, and then check if that's consistent with the classical ensemble interpretation.
I guess those things will all commute with each other because they're just like separate boundaries. There's no operator ordering of those things.
Yeah,
so
you need to put two correlators on one side which don't commute with one another, and then compare the correlation of those two operators on one side which don't commute with their correlators with two operators on the other side which also don't commute with each other. So that's the kind of setup you would take for a Bell inequality.
Okay, how specific do you have in mind?
No, I don't have anything specific in mind. I was just trying to think more about the question of whether the ensemble interpretation is itself consistent, and whether there are more consistency conditions one could put in it. I mean, I see in some specific examples it is, but for the more general story.
The more general story, I don't know. Your example sounds interesting. I want to hear more about what you were thinking about.
Well, I was thinking rather than just compute the partition function, one could try and compute like correlation functions. Yeah.
Are you computing it's a commutator of the operators, or just 2-point function of two non-computing operators on two separate boundaries?
Yeah, so it would be 2-point functions, but 2-point functions of so you take A1, B1 and add to it like A2, B1. So let's say A are the operators on one side and B are the operators on the other side.
Okay.
So on both sides, you take some operators A1 and A2 that don't commute with each other, and B1 and B2 that don't commute with each other.
Okay.
And then you compute some sum of, you compute some CHSH kind of sum of 2-point functions. So you compute some combination, I think, which looks like A1, B1 plus A1, B2 plus A2, B1 minus A2, B2. And then there are some limits on how large that can be if there's a really a probability distribution. And you might I don't know if it's possible, but one could ask a question of this kind.
Well, I haven't thought about it at all. It does sound interesting.
Okay, yeah, maybe we can talk more about it offline.
I guess the example where this has been shown to be consistent with an ensemble is one where there are no operators at all except for the partition function.
Right.
So you're right that there could be some constraints in cases where there's operators.
Right. The issue would be that, and the reason this might be relevant is because if the wormhole is somehow indicating that there is, I mean, it shouldn't indicate there's an entanglement between the two sides, right? You don't want there to be,
right,
you really want to say that. And this is the kind of probe that would check for entanglement between the two sides, I mean, by computing correlators. So it would rule out, the fact that you're somehow, it would rule out the ensemble versus the entanglement between the two sides.
I wonder if we can argue. Okay, the kind of argument I want to make is that you cut the wormhole in half, and we describe the connected wormhole as a sum over boundary conditions. And then we just say that that sum is a classical ensemble. So then it sounds like it's okay. Like,
but you're summing over correlated. I mean, the cuts are the same on the left and the right. Right? It almost sounds like inserting a complete set of states. Which should
yeah. So let's do that. That's
but
exactly.
That shouldn't be enough to differentiate between entanglement and classical probability.
But isn't it? Won't the computation for fixed values of those things be just an ordinary quantum calculation, and then we're explicitly doing a sum over those?
Yeah. Maybe. Yeah. Okay. Maybe. I mean, I should. I mean, the only concern I had was that somehow we shouldn't be. It shouldn't be like some ER equals EPR story, that somehow this computation comes along with entanglement, and that's the only thing I wanted to rule out with correlators. But yeah. And maybe we can talk more offline about this. Yeah.
Okay.
Hi,
Rajesh.
Hi, Douglas. Nice talk. I had a very naive question about this general issue that's cropped up about super Yang-Mills and the ensemble average. So I was wondering if the following makes sense. If we consider something like n equal to 4 super Yang-Mills and think of the partition function of super Yang-Mills with arbitrary sources turned on for all the gauge invariant operators, starting with, of course, the stress tensor, but then all the other stringy modes as well. And this is morally supposed to be some kind of string field theory partition function, which for all those sources. In some way, does it make sense to then think of integrating out all the massive modes as some kind of an averaging, effectively averaging for the gravity mode? I mean, in some sense, it would so in a way, is string theory a sort of, is that self-averaging that is there in string theory? Is that like an ensemble average? And could that function like an ensemble average effectively in some sense without it being really an ensemble?
Wait, but why are you averaging over those things?
No, you are integrating out. So like in the path integral, the string field theory path integral, you are integrating out all the other modes, the massive modes, but they're all coupled to gravity. So you're effectively kind of, it's like gravity.
I wasn't clear on whether you were integrating over sources or just doing the path integral over those fields in the bulk.
The path integral over this. So I started with the n equal to 4 Yang-Mills with the sources, but those were the boundary sources. But then in the bulk interpretation, yeah, in the bulk interpretation, yeah, you integrate over all the bulk fields with some definite source terms at the boundary, but I was wondering whether there's some sense in which that bulk integration effectively of all these massive string modes functions like some kind of self-averaging in the bulk, so it could massive string modes essentially do that because of the fact that they are?
I guess somehow it's hard to see from the bulk whether the theory is describing an ensemble or not. And what we would need to explain these wormholes is some kind of ensemble in the boundary. So it would be something like integrating over the boundary sources, not integrating over bulk fields. Integrating over bulk fields, well, you get some bulk theory, and it's not clear from the bulk theory whether it's describing an ensemble or not.
Yeah, I mean, normally you, yeah, I guess you don't turn. I mean, you don't turn on the sources for all the relevant fields and do much with them. But yeah, but I was wondering whether that there's some effectively you're somehow averaging over the sources of these boundary fields, but in the of the boundary sources. But again, yeah, it's a little vague. I'm not sure.
I mean, it's true that somehow, I guess, part of what you're getting at and what other people have been pointing out is that, like, you need to do the right kind of averaging. It's like you don't need to average a small amount over some kind of tiny, insignificant noise. And shouldn't there be some way that we're just making a tiny error, and that, well, can it be explained by some tiny error? And I'm not sure, well, hopefully so, but I'm not sure exactly how.
I should let Rajesh finish, but I wanted to.
Go ahead, Sandeep. Yeah.
Just to pick up on what you said, Douglas, could it be the following? If you take closed type 2B string theory, which is the dual background for the n equals 4, there are all kinds of very complicated non-perturbative effects that you would actually have to sum over to get the e to the minus s or s over 2 type of correlations correctly.
Yes.
Yeah, that I think we would probably agree that there are all kinds of, things we barely know about even. But now, suppose you were trying to get away by just keeping Euclidean gravity wormholes, or let's say gravity wormholes. Is it that all the other stuff can be incorporated as some kind of an effective theory for gravity once you are including the wormholes, with the understanding that that's doing the coarse grading needed? Sorry, very vague statement, but this is the kind of thing which might be happening.
But again, that sounds like you're trying to get an ensemble in the bulk, not on the boundary. I guess I mean, okay. You're right. So we're discussing some exponentially small effects, e to the minus s effects.
Yeah.
And there's all kinds of stuff that we should do first in the bulk before we start doing wormholes. And so on the one hand, that could lead you to think we just shouldn't trust the wormhole computations at all. But they do give something that's kind of right.
Yeah.
And in particular, in the page calculation, they give something right. And we would like to understand whether we should take them seriously and what cost we have to pay to do so. If they didn't give the right answer for this page curve and for the average of the spectral form factor and stuff, I personally wouldn't be very motivated to think about them or to think about ensembles or anything like that. I would say just, we have to understand the full bulk theory. Let's try to do that. But since they do give something reasonable, we end up struggling trying to interpret it.
Yeah, no, fair enough. It's remarkable. Actually, what I would say is what your work shows is, to turn it around, it's remarkable that you get anything right, and so much right from the Euclidean wormholes. You get the page curve turning around, which, as you said on your first slide, you just wouldn't have expected. So I think it's actually the other way around, that you're getting so much right is kind of amazing.
The thing that keeps me up at night, and though, is that maybe it's wrong. Like maybe the wormholes are wrong, and they're not the first step in the right direction, and we need to include fuzzballs or whatever. And but I don't know.
Thank you.
It would be nice to have some other cases where. Oh yeah, sorry. Go ahead, Spenta.
No. Please finish. I mean, I'm sorry.
It would be nice to have some other case in physics. Maybe somebody knows of an example where there's a controlled calculation of some kind of complicated quantity where the first term is some kind of average of like, but it's not just an effective description. Like it's actually an honest calculation where the first term is some kind of simple average. The Selberg trace formula is sort of like that, but it'd be nice to have something closer. Anyhow, so, sorry, please go ahead, Spenta.
Yes. So it's a slightly technical question. In your work with Shankar and Saad, the random matrix theory that you worked with was a very complicated one, actually. But in today's discussion, for the late time answer, you just were working in terms of a Gaussian ensemble for the matrix element Wij. Can you just indicate how that happened actually? So is it a late time issue?
Yeah, I think it's because I was focusing on just this cylindrical contribution. I think probably if you try to compute higher topologies, you end up having to interpret them as some more interesting ensemble. But if you're just trying to compute this leading thing, then the Gaussian approximation is enough to explain it.
I see. So the ensemble depends upon the complexity of the calculation in some sense.
Well, I guess the calculation we're doing is simple and it's not probing very much about the ensemble. It's just probing like these Gaussian moments. And if we did a fancier calculation, we would learn more about the ensemble.
I see.
Hi, Douglas.
Thank you. Yeah.
Spenta, are you done?
Yes, I'm done.
Yes. Okay, first, thank you so much for this talk and for staying awake repeatedly to give us talks in India. Thank you very much for that. Okay, now I had a question which I'm not sure how precise it is, but let me ask it anyway. These inner products you were computing of black hole states with insertions are inner products between states which, at least roughly speaking, are states in one-to-one correspondence with the Hawking radiation, right? Because for every Hawking radiation mode, you've got a state.
Yes.
And the statement that the inner product itself appears to be orthogonal unless you square it. Would basically be the statement that would basically seem to require that your Hilbert space of the black hole was also in one-to-one correspondence with the Hawking radiation.
Yeah, it would have to be at least as big as it.
At least as big as that. Okay, and when you square it, what you're doing is seeing that that was not right.
Yes, exactly.
That it was actually a smaller Hilbert space, right?
Yes.
Now, this was reminding me of something we've seen before in n=4 Yang-Mills. If you create a Hilbert space just by acting with traces, which are like the Hawking radiation modes, you get a Hilbert space. But sometimes acting with just the traces gives you too large a Hilbert space because of trace identities. It sort of feels a little bit like the bulk is not seeing the trace identities in the 1-point function, but is starting to see it in the 2-point function. In the old days, people called this the stringy exclusion principle. In ADS, there was some sort of understanding of how that came about directly in the bulk. So some sort of finite k for the Wessumino-Witten for the SL2R or the SU2 or something like that. So I don't know if I don't know what my question is precisely, but I thought I would throw these words out and hear your reaction.
So what is the? Oh yeah, go ahead.
So your question is precisely about finite n, Shiraz, right? In finite n, there are all these relations amongst these gauge invariant operators. Am I right? At n equal to infinity, this will not matter because of factorization.
That's right. So everything here is some sort of finite n effect. The trace identities cuts down the effective Hilbert space.
Yes.
And at some point, you feel states that you thought were independent and looked orthogonal actually are not independent and orthogonal because of these trace identities. And I was wondering if what you were doing.
Uh-oh, I can't hear Shiraz.
Yeah, I think we've lost.
Yeah, maybe meanwhile, can I ask a question, Douglas?
Oh, wait, I think he's back. Shiraz, are you back?
I'm sorry, my internet fluctuated. Yes. Yeah, so I was wondering whether, I'm sorry, Gautam, but yeah. I was just wondering whether somehow what you're doing is searching for the gravitational the gravitational expression of these trace identities. And I don't really know what more to say, but that's what I was.
Yeah, that's exactly, like you're looking for gravity to tell you that this is an overcomplete set of states. And so for the case that you were describing, how does this work? It's like some high, if you have too much momentum.
Well, yeah. I only vaguely remember. Yeah, there were 2 or 3 different stories depending on the situation. The simplest situation that, again, I vaguely remember was that described by Maldacena and Strominger very long ago in ADS3. And they talked about how these trace identities were somehow accounted for by the fact that the bulk, if I remember right, I think Rajesh will remember this better, but that the bulk string worldsheet theory was a Wessomino-Witten theory at finite level K. You know, the truncation of the operator spectrum there mimics these trace identities. And then there was, in ADS5, there was some story involving giant gravitons and so on that was a little more vague. I would have to think hard to see what, or maybe read hard to see what people said about it earlier. But there was some discussion on it. I was wondering whether that would be relevant.
So in the ADS3 case, this was just, it was a limit on the number of the, basically of the single trace operators you can have that are related to the vertex operators.
Yeah, it was similar to what you'd get if you had just trace Z to the K in n equals 4 Yang-Mills. Right, okay. You take Z to the power K and insert them for an arbitrary K. But once K goes over N, you're just overcounting. Right, I mean, from the boundary, that's clear. I think in ADS3 there was some story of a bulk version of this, and perhaps there's also a story of some discussion of a bulk version of this in n equals 4 Yang-Mills. But it's maybe LLM is a bulk version of this for the half research.
The only thing I think what you're saying is in spirit. I think what Douglas was saying. The only thing that bothers me is sort of these would seem like D-brain effects because they are of order n, or potentially contributing at e to the minus n rather than e to the minus n square. But I think they are probably similar in spirit. But yeah, whether they would exactly be the same, I'm not very sure.
You know, when there's only one matrix involved, everything gets truncated at n. But as we see when we compute the free Yang-Mills partition function, the effect of trace identities really becomes important at n square. I mean, these identities arise already at n, but they start having qualitative effect only at n square. Right, we see that from the partition function of free Yang-Mills computed on a sphere.
You mean they would cut down states significantly at...
They change the n square part of the scaling.
Yeah, because at order n, it's probably an order 1 correction, but at order n square, it's probably an order n square correction. Yeah.
Yeah, Shiraz, this story indeed appeared for the LLM case as well, for dual giant gravitons, where the Hilbert space of the dual giant gravitons itself was truncated because of this finite n effect.
Can I just follow up on what Shiraz you were saying and ask you and Douglas? You know, in a case, it does seem to me that finite n is important, right? Like all of you are saying in this, and the effects are probably e to the minus n square. But is there an example from, say, ADS3 or something, where we could do the following? We know there are these set of constraints, and we try to mimic them in a gravity approximation, which will probably necessarily be crude. But we show that the extent of crudeness is not to discard everything interesting, but to keep some average features right. Could we, in other words, what would be very interesting for me is there's a context well enough controlled that we know when you keep the actual effects which arise in string theory, you have a unitary theory, etc., etc. But you're powerful enough to then construct some kind of gravity approximation, and you see the kind of story that Douglas is finding. Is this out of question in ADS3 or something? Sorry, I know very little, but just to ask you. Or well, Douglas should go ahead. Sorry. Douglas, please go ahead.
No.
I don't see the connection between finite n and this ensemble average business. I'm not able to see the connection between the constraints on the space of operators and the fact that the gravity evaluates in terms of a distribution ensemble.
Well, I think what Shiraz was pointing out is that the underlying effect. So gravity is computing some ensemble average of some effect. Forget about the ensemble average for the moment. The basic effect is that the black hole appears to have too many different orthogonal states. And so we're looking for a bulk mechanism that can tell you why it has fewer states than it looks like it has. So that's something that arises at finite n in various contexts. One thing, I don't know if it's relevant or not, is I feel that the way in which you see the Hilbert space is smaller for the black hole, it's going to be like really complicated. The inner products between these states are going to be really complicated. Is there that
suppose,
kind of, yeah.
Suppose we looked at this in the LLM context. It's a very simple toy model. We're building the half BPS Hilbert space. Right, that is just completely understood from the bulk. There's no black. But I think both sides are completely understood the fact that there's a, naively once again, you could put arbitrary numbers of gravitons. Each of the trace z to the k's could be excited independently. But, there's some back reaction in the bulk that makes that not true. And this is understood in great detail. So that give you some lessons. Or is that too simple?
Well, I don't know enough about it to comment intelligently, but it sounds like an interesting thing to look into.
So Shiraz, like in this LLM, has anybody studied like two boundaries and asked whether what what corresponds to wormholes and whether they are there or not there. I guess that would be the question.
That would be one version of the question, but the two boundaries is only when you want to get this thing squared, right?
Yeah, but that's kind of closest to what.
No, that's right. So that is one way of curing the problem. But it sounds to me like a very roundabout way of curing the problem. You'd like to cure it just in the one boundary case, right?
But if you cure it in the one boundary case, somehow you need to get this random matrix out of the bulk. The random matrix of inner products.
Yeah. So in a situation which is very crazy, you maybe don't have a hope of practically doing that. But something like LLM, where the spectrum is not random at all, it's just half BPS in Hilbert space, but you still have the cuts down, where you could hope to cure it just in one boundary case, and they have done it, right? I mean, you could just ask the question, how does the bulk see that this Hilbert space is the Hilbert space of the trace the matrices including trace identities? The bulk sees that perfectly. Well, I'm not sure it's the analog of your question. I'm not sure it's close enough to what you actually want. But this question has been answered.
Isn't there more to what Douglas is saying? Wouldn't we have to show not only that the bulk cuts it down, but that the gravity approximation gets some crude version of the cut down, right?
Yeah, and in LLM, gravity gets everything right?
I see. I know very little about that story.
I guess the challenge for this, or for discussing these microstate geometries or fuzzballs more generally, is connecting it to the black hole. It's like you have some bulk description where you have these states manifest.
Yeah.
And from that end, the challenge is connecting it to Hawking's calculation somehow.
Yeah. So you're saying that we're doing this in a sector which is too simple. With the too few states, we don't really have a black hole here, and so the mechanism may not carry through.
Well, may not, but it may. I mean,
yeah.
Somehow I feel like it must be the case that we need to try to understand how they can be bridged, right? There's a whole community of people that work on this, that trying to understand black holes starting from microstate geometries. And I don't know anything about the literature, but it seems important.
Okay. Thank you.
No, thank you for the comments. And I'm worried that as time goes on, I get just sort of slower and stupider as evening progresses. You guys are just warming up, so.
I'm really sorry for keeping you so long.
Yeah.
No. I don't mind. I'm just making excuses for myself.
So just one final question I have, Douglas. Sorry, it's that this last question Shiraz raised about finite n. It's not very clear that the finite n aspect, which cuts down the degrees of freedom due to these identities, is directly connected to the ensemble calculations. Or am I missing something, actually? That if you work with finite n, you don't have ensemble, or what? I don't understand this point, actually.
I think it's different. Shiraz is saying, forget about wormholes, forget about ensembles. Just try to compute this inner product correctly in gravity somehow. And we have no idea how to do it for the black hole, but maybe you can do it in a simpler theory, or for some small subsector of the black hole states. So he's suggesting a different way of explaining the page curve physics, not based on wormholes, but based on microstate geometries. That was historically, at least up until a couple of years ago. I mean, it was thought that that was really like the only way we were supposed to do this. We have to understand the microstates in the bulk, and then we can understand the page curve. And in the last year, we saw that we can understand the page curve using wormholes. And did we really get closer to understanding quantum black holes or not? I don't know. Shiraz is suggesting we go back and try to get a more microscopic understanding. And maybe that's necessary.
And maybe once you've done that, you can see in what sense there is some sort of, you know, some aspects of the answer are approximated by an answer.
Right.
Yeah.
Mm.
Right.
Yeah.
Yeah. Okay.
Can I quickly ask something naive?
Yeah, please go ahead.
Yeah. So if the question is about like the theme, whether gravity is doing some ensemble average and so on, is there a naive setup without black holes or something, maybe in thermal ADS or vacuum ADS or something, where you can probe this question, like, as in the theme should be general, right? Whether gravity is doing an ensemble average calculation or not.
Yeah, that's an interesting question. I feel like maybe it only has to do with these, to the extent that gravity describes an ensemble, maybe it's only having to do with these black holes and the high energy states, where there's lots of states and there's this chaos and there's a kind of reasonable ensemble. And maybe all elements of the ensemble would have the same low energy physics.
So but off the top of the head, like we can't come up with a probe which is close to the vacuum and so on, which would check if a theory is like ensemble average or not.
No, not immediately. One thing that might be kind of related. Suppose you take, okay, so a theory that is dual to an ensemble is JT gravity, but let's not study JT gravity. Let's study n equals 2 supersymmetric JT gravity. Then there's a bunch of BPS ground states, and those things are not fluctuating in the ensemble. So there's some kind of fixed low energy stuff that is not fluctuating, and then the rest of the spectrum at higher energies is fluctuating. So maybe you could imagine gravity could describe something like that, in where the low energy stuff having to do with vacuum ADS is not contaminated by the ensemble.
Okay, thank you.
Sorry, Douglas, can I ask
yeah,
a
please.
question? Yeah, so if we go back to that ETH question, I mean, so can we go back to that slide once more, where you did the matrix elements and replace that by some ensemble averaging? So the matrix elements of Wij, Vij, that kind of stuff.
Okay.
Yeah. This one. Yeah. So yeah, I can't see very well. Can we go to the full screen, please?
Oh, we can, but it's going to. I have to do a different window. Let me do that.
Okay, so I can.
Here. How's that?
Great. Thanks a lot. Yeah, so I wanted to, okay, so I realize now that, you know, W's are not Hermitian operators, W's and V's, so I can't apply ETH directly. But, so then I have this, you have this, you know, ensemble, so you have the matrix elements right below the diagram. And then you say the Wij, the ensemble average of that is 0. And the Wij, Wi prime, J prime, the ensemble average of that is some thing.
Mm-hmm.
So can you perhaps replace these ensemble average things by something saying that they are like random variables in some way that you do for ETH? What I mean to say is that in ETH you could say that the matrix element like Oj, where O is a Hermitian operator, Oj is something diagonal plus some you know, e to the power minus s or e to the power minus s by 2 times a random variable.
Yes.
So this is saying something about specific field theory models and not any ensemble averaging. It just so happens that the Hamiltonians of those models are such that the matrix elements behave that way. That's something to be proved, etc. But you don't introduce an ensemble. I'm saying that these two ensemble averages that you have, you might as well have perhaps replace them by some behavior that is expected out of the Hamiltonian of this model or something like that. So what I mean to say is that the computations that you are doing are actually the computation of the density matrix itself. It just so happens that the sum over this IJKL states are making them look like an ensemble average. Is that a correct way
well,
of
I think it's a reasonable idea, but it turns out not to be true for this quantity. So
I see.
This is a quantity where that won't just depend on the basically it's not a self-averaging quantity. So the logic that you were proposing would be correct for a quantity that is self-averaging. And for that case, you can replace this ensemble here by just the sum over I and j. That's like a good enough ensemble. And for this quantity f, it's not true. So it depends what you're trying to compute. And for this thing, it's not true. For this thing, in order to apply this formula, you really need to assume there's an ensemble.
I see.
But
so is it? So I don't see that. Is it obvious that it's not self-averaging? I mean,
well, actually, yes, because let's just study one of these things. So f is a product of two factors. F is, let's call it g squared.
Right.
And let's just study g. G is some quantity that has zero average in the ensemble.
Okay.
And if f is g squared, where g has zero average in the ensemble, then f is never self-averaging. So if you just take something that has zero average in an ensemble and you square it, that thing will never be self-averaging. It will have a non-zero average value, but it will fluctuate around it. So that's the reason why this f is not self-averaging.
Oh, I see. I see. So this is where you must introduce an ensemble. I see. So
yeah. So that's why this quantity, the answer that gravity gives for this quantity is like only an answer that makes sense with an ensemble. It can't be explained just by like ETH formulas.
I see.
By the way, is there something wrong with ETH works for non-Hermitian operators, right? Like, I don't think there's a problem with ETH. Because
yeah, I don't remember now that, but does it work for? So I thought that the main difference why you can't use it here, as you explained, was that this W is not a positive definite. Yeah, that part I don't remember, but I thought that's what you were saying, that W is not a Hermitian operator.
I think basically what I was saying there was just explaining that this G has zero mean. So that's what I was trying to explain before in kind of a roundabout way. But the important thing is that f is g squared, where g has zero average value. And I was trying to explain why g has zero average value. But yeah.
So if ETH does work for non-Hermitian operators, then okay, the examples that I remember are of Hermitian operators.
Well, but I mean, if it works for Hermitian operators, you can make a non-Hermitian operator by a sum of two Hermitian operators with complex coefficients. So.
Yeah.
Or if you like, we can take our non-Hermitian operator and decompose it into Hermitian, anti-Hermitian
Yeah, that's true. So then, yeah, so then I'm still confused. Maybe some simple point I'm missing. I'm still confused why Wij. I cannot apply ETH to Wij.
Well, let's consider a simpler thing. Let's take okay, how about maybe we can do
but if W is just an annihilation operator, then of course I don't see how that trick of writing it as Hermitian plus I times. Oh no, that will work. I'm sorry, excuse me. The annihilation operator is just some P plus IQ or something. Yeah. Phi plus I pi.
Okay. It's past midnight for Douglas.
Oh, I'm so sorry.
Well,
oh no, it's only 11. It's only after. It's not at midnight. It's only after 11. But
okay.
I'm just. It is. I am normally no.
Thank you very much.
Anyway, so I just wanted to make sure that you need the ensemble rather than just replace those things by some random quantities.
Yeah, that quantity there is similar to the it's similar to the spectral form factor, in the sense that the answer is not self-averaging. So the answer that gravity gives you has to be interpreted as an ensemble average.
Thank you.
Yeah, well, thanks a lot for all your comments. And it was fun.
Thank you very much.
Thank you very much for appearing second time in a couple of months in front of us.
No, it was a pleasure.
Much, yeah. So, yeah. Thank you so much. Yeah.
See you again soon.
Thank you, Douglas.
Yeah.
Thank you very much.
Thank you very much. Yeah. Bye. Bye.
Bye-bye.
Bye. Bye. Bye.
Bye, you guys.
Bye.
Bye. Bye.